Okay, thanks a lot for the invitation. It's a pity that I cannot speak French. I speak it very badly, so I'll have to talk in English. Let me first thank the organizers of this prestigious seminar for inviting me to give a talk here. It's a real honor. Well, in the title you see that I will talk about the Hele-Shaw asymptotics, so let us first explain what the Hele-Shaw problem is. Well, Hele-Shaw, it's just one person, Henry Sidney Hele-Shaw, who in 1899 proposed a model for the injection of an incompressible fluid between two flat parallel plates which are very close one to each other. And so in his model, well, the density in the fluid is constant, so you only want to know what's the pressure. And where you have a region, you are injecting fluid at this point, for example, and at each time the fluid occupies a region omega of t, and in this region the pressure is positive, and well, the pressure is a potential for the velocity, and so here p is harmonic, okay? And well, at the boundary, if you have surface tension, if you don't neglect it, the pressure will be proportional to the curvature. Okay, and then the fluid, I mean, the free boundary, this is the free boundary, the boundary of the domain omega of t. The boundary moves with the fluid. So here, since the pressure is a potential for the velocity, the normal velocity will be given by the normal derivative of the pressure. Okay, so at each time you have a region, there you can compute. Well, in fact, here you are injecting, so you will have a delta here, so that p is not trivial. So you're injecting fluid. At each time you compute a harmonic function, the solution of an elliptic equation, and then you compute the gradient at the boundary, then you move the domain, and then you start again. Okay, so this is the model. And the thing is that we want to develop these kind of models for tumor growth. So the idea is that we will have a region occupied by the tumor, okay, omega of t. Here we will have an elliptic equation, say Laplacian of u equal to something, Laplacian of p equal to something, so that p is non-trivial. And then the boundary is moved according to this rule. Normal velocity equals to the normal derivative of the pressure. Okay, this is Darcy's law. And well, we'll neglect for the moment surface tension, so that p equals 0 at the boundary of this domain. Okay, so this is an incompressible model. The thing is that we want to approach this incompressible model starting from compressible models for tumors. And we'll make things more and more incompressible, and in the limit, we'll get such kind of description of the tumor. Okay, so this is the kind of things we are trying to do. Okay. Okay, it doesn't move. Okay, let me Control L. Okay, so this is a project that we started with Juan Luis Vázquez and Benoit Pertam. We started with some simple models, and we talk about them in this talk. And well, the results have been published at the beginning of this year, and we continued with the project trying to introduce more elements in the modeling, and some other people are involved, like Nicolas Bochelet and Mintang. And well, we produced a paper. I don't know whether I will have time to talk about it, which will appear in December. And we are still working on this with some other people, like Antoine Mellet. And well, let me give you some figures. Everyone is aware that cancer is a major health problem, but well, just some figures. It's now, since 2004, the main cause of death in France, cancer. In the USA and Spain, it's not the first one, but it's close to the first cause of death, which is heart diseases. In Spain, at least, it's the first cause among men, and in the USA also. Okay, the percentage of deaths caused by cancer is increasing, and well, the number of cancer cases is increasing also. This does not mean that there's no improvement. I mean, in fact, the rate of survival, which is measured by the survival rate of the survival percentage after 5 years, 5 years after the cancer was detected, is also increasing. So there's no contradiction in this. It's just probably that, first of all, that things are improving more in heart diseases. And the second thing is that the possibility of developing cancer if you are old are much higher than if you are young. And then if you don't die because of other reasons earlier, then you will, it's more, you have more probabilities of having cancer. Okay. So anyway, well, it's becoming a more and more important problem, cancer. It's not that cancer appeared just some years ago. Cancer has been detected in bones of dinosaurs from ancient ages. But, well, more or less around 1970, people were really aware that something should be done against cancer. And, well, maybe the National Cancer Act, which was signed by the then President of the United States in 1971, was like a kind of milestone in the war against cancer. And, well, then a lot of money was put into research for cancer. And, well, for mathematicians, we have a challenge, and it's to develop mathematical models and simulations in order to both describe and predict the evolution of the disease and to predict what is the best treatment. Well, and a bit after this date, 1971, just a year after that, it may be a coincidence, but it may not, a guy called Greenspan produced the first diffusion model for tumor growth. Okay. Well, in the name, you see that he says solid tumor and diffusion. So we will talk about this kind of models. So we will describe continuous models for solid tumors. So we are assuming that there's a large number of cells. Okay. We are leaving out discrete models. There are discrete models if you want to describe cancer at the molecular level or at the molecular level. But we are leaving this out. And we are only going to talk about solid tumors, which are developed within an organ. So we are leaving out models for blood cancer, leukemia, and lymphatic cancers. So the typical radius of a cancer cell is around 10 micrometers. If you have a small solid tumor, it will have a radius of around 1 millimeter. So that's 1 million cells. So we have a pretty big number of cells. Okay. So in the first models, the models by Greenspan and the first ones, it was assumed that cell multiplication, cancerous cell multiplication, was limited by nutrients, nutrients that were brought by blood vessels. Nutrients are glucose, oxygen, several things. Okay, and there were in these earlier papers two kinds of descriptions: a compressible description describing the dynamics of the cell population density, which may change, and incompressible models in which the density is assumed to be constant. And there, what you do is you describe the motion of the tumor geometrically. What you have to do is you have to describe the region occupied by the tumor. The density there is no longer an issue. And, well, what you want to know is what the pressure is there. Okay. So in this incompressible description, you get one of these free boundary models. But then when the tumor reaches a size 1 millimeter, then it's not so easy for nutrients, for the cancer cells to get nutrients, and they start to die because of lack of nutrients. So they become necrotic. Okay? But then the thing is that necrotic cells send some signal that makes the body produce new blood vessels. This is called angiogenesis, and then these new blood vessels give enough nourishment to the tumor again. And, well, the problem with this is that then cancer cells may go to other parts of the body through these blood vessels, and this is metastasis, and, well, that's a big problem. Okay, so let's think that we are in a states where you have enough nourishment, so that's not an issue. And then we will only talk about mechanical issues. Okay. So we're going to talk about, first of all, about mechanical models, in which there's enough supply of nutrients. So the problem here is competition for space. Cells do not want to become close together, and in fact, there's a mechanism called contact inhibition that makes cell multiplication stop. It prevents cell multiplication when you reach a certain pressure. Okay. And there are again two kinds of descriptions: cell population density models and free boundary problems, and we want to relate both kinds of descriptions. So cell population density models, they are incompressible models, and free boundary problems we are thinking about. But no, so these are compressible. These ones are incompressible. So we want to pass to a certain incompressible limit or a stiff limit. Okay, so we will start by the compressible model. So here you have the continuity equation, and well, there's a right-hand side term of Lot capital type that well, if the density is 0, there will be no multiplication, of course. But in the places where you already have tumors, the multiplication will be proportional to the density, and well, you have a factor here taking into account the pressure. So this factor phi of p, it will decrease with the pressure. The bigger the pressure, the smaller the multiplication, and you have an initial data. So the rho is the cell population density, the p is the pressure, and we are assuming that cells are only pushed by mechanical forces. In fact, we are assuming more than that. We are assuming Darcy's law, so that the velocity is given by the gradient of the pressure minus the gradient of the pressure. Okay. As for the function phi, as I told before, well, it should be decreasing with p. In fact, we will take it strictly decreasing with p, and that there's a threshold pressure, what is called the homeostatic pressure, which is a positive pressure, which is the lowest pressure that prevents cell multiplication by contact inhibition, where phi equals 0. Okay. And then, well, to close the system, we need a constitutive law relating the density of the pressure. Well, the important thing is that pressure increases with the density, okay? But we'll make a definite choice here, so that makes things simpler, okay? We'll take a power, but things can be done for other functions. So here, the pressure, well, here we have a harmless coefficient m over minus 1 that's introduced to make things simpler. And here you have the power m minus 1. And here you have a rho c, okay? And m is bigger than 1. So let me draw. Well, you can always set rho c equal to 1 by a change of scale. And well, the thing is that here, let me draw rho in terms of the pressure. So here you have this threshold rho c. And then the thing is that, well, you get here something like this for a certain m. When you increase m, so this is m1, when you increase m, what happens is that below the level rho c, things become bigger, and above it, they become smaller. So what do you get in the limit when you send them to infinity? In the limit, you get a density that does not depend on the pressure. So this is the incompressible limit we are looking for. So this is rho sub c. Okay, in fact, in the limit you might get things, you might get values of rho different from 1 and 0 if p equals to 0. So here you have a graph. Okay, this is important. You have a graph, okay? And well, this is called the Hele-Shaw graph. Hele-Shaw graph, Hele-Shaw graph. Okay. So what we have is, with this choice, we have the well-known porous medium equation in this side with a reaction term. Okay, so this is well-known. And the thing is that we are letting m go to infinity, so we may even allow the initial data to move with m. Okay, but well, they have, since we are looking for convergence, they have to behave well in the limit. So we have to ask for some conditions. So we will ask them to converge to something in L1, some fixed thing. We will ask the initial data to be such that the pressure of this initial data is below the threshold pressure above which you can have, well, cells you do not have cancerous cells above this pressure. And well, this is important when passing to the limit, because this will mean that the limit initial data will be between 0 and 1. And this is quite important because, well, this limit graph is incompatible with values of rho which are above 1. So if the initial data were above 1, well, you may pass to the limit, but then the first thing that happens is that the initial data are projected onto something which is compatible with the limiting graph, and then you have an evolution, okay? And well, you have initial layers, you have all kinds of things. We want to avoid this because this is not important for the tumor growth model. But well, this analysis can be performed, okay? And then we have some kind of technical assumption. We want to get BV bound, so we will ask the initial data to have gradients bounded in L1. So indeed, there's a limit here. Okay, let me write somewhere the equation before passing to the limit. What we have is that dt times rho m plus the Laplacian of rho to the m, rho m to the m equals rho m times phi of pm. So if you let m go to, and let me remind you that pm equals m over m minus 1 times rho m to the m minus 1. So the pressure goes like p to the m, so this goes more or less like the pressure, and what you get in the limit is really, you get this equation. You get that you can pass to the limit both in the density and the pressure, and the limits satisfy the limit equation, okay? But the point is that, this is what I'm saying here, the point is that P and rho, which were related by a function before passing to the limit, in the limit are related by this Hele-Shaw graph, okay? And well, you have other things here. It's because of our choice of initial data. Well, this is more than because of this choice. The limit density will be between 0 and 1. The limit pressure will be below the homeostatic pressure. Well, the initial data are the limit initial data. And well, where is it that we have convergence? We have convergence in L1, both for the density and the pressure. But about the limits, well, the limit for the rho is a continuous function with value, is continuous in L1, and it's a BV function. But well, the limit for the pressure is not a continuous function in any LP space, but it's still a BV function. Okay, so let me explain what kind of strange things may happen. Well, before explaining that, let me tell you a kind of other things. Well, so the limit graph is that one. That's what I explained. Well, this is written in the other way. So if you put here the pressure and here the density, it's like this, the Hele-Shaw graph. So, well, this is just an easy computation. You compute rho m times pm, and you have that thing on the right-hand side. If you let m go to infinity here, you will get this goes to 1 and this goes to p infinity, so you have this. But the point is that in order to show that you are in the Hele-Shaw graph, you need to have a strong convergence. And that's not that easy, okay? In some cases, you really need a strong convergence. You cannot pass to the limit in both things, in rho and p. Okay, so let me explain the funny things that happen for this model. The diffusivity before passing to the limit is given by m times rho to the m minus 1. So if rho is above 1, the diffusivity becomes huge, and that's why things collapse below the level 1. While if rho is below 1, the diffusivity becomes very small, okay, and things do not move. Okay, so things will only move when rho is equal at the border of this region, okay? So in fact, well, one can do an analysis if the L infinity norm of the initial data is above 1, but then we will expect we expect convergence, again, to solutions of the same problem, but not with the same initial data, but to a projected initial data that is compatible with the limiting graph. In fact, this has been done when there's no reaction, and it can be computed, the projection, in terms of an obstacle problem. Okay. So let me. Well, I was claiming that in the limit we will get a free boundary problem. I have not seen it anywhere yet. So let me explain where it comes from. If you can write the equation for the pressure, and you get this nice equation here, okay, and you see terms with an m in front of them, this one and this one. So at least formally, if you are able to control this and this, if you let them go to infinity, what you will get is that only these two terms remain, and you will get that p times Laplacian p plus phi of p equals 0. So you have two regions, the region where p is positive. This is the region where p is positive, and in this region what you have is an elliptic equation, this one, okay, which has a natural solution as well. And here you expect to have p equals 0, okay. And well, in this we can improve. We can indeed prove this in an H1 sense. In fact, what we get is that the integral of the minus gradient of p infinity squared plus p infinity times phi of p equals 0 for almost every t. But let me tell you that proving this is equivalent to proving the strong convergence of the gradients in L2. And let me also point out, or I will talk about this, that the main difficulty is the lack of time regularity. Lack of time regularity for p. So let me explain you which kind of things may happen for the p. For example, in this case, imagine that you have two tumors that meet. So imagine that you have a tumor here and a tumor here. Okay, so these things are advancing. Okay, and when these two things meet, okay, then now the domain occupied by the tumor is this bigger set, and then the thing is that since p is a solution of this elliptic equation, p will jump immediately here. Okay, so you will have an immediate jump of the pressure. Okay, and well, this leads to you have very poor regularity in time. Okay, so that's the difficulty here. Well, so we will expect to have a free boundary problem. So the region occupied by the tumor is given by the region where p is positive, and in fact this has to coincide with the region with rho equals 1. Well, let me explain this in a moment. In principle, you could have regions where rho is equal to 1 and the pressure is not positive, but we will exclude this in a minute. So in omega t, you have this equation. The p infinity will be in H01 of omega t. You can solve this, but let me. Okay, this is. I'm handing waves. I'm waving hands. I'm sorry. Here, well, if so, the leading terms are this one and this one, but if you are close to the free boundary where p is 0, then these two terms are not there, and then what you will get in the limit is a hyperbolic equation. If you are looking at the free boundary, and it is this equation. Okay, so at the free boundary you have that the time derivative of p equals the gradient of p squared, and well, this is now to be equivalent if the free boundary is a smooth hypersurface to having a velocity given by the gradient of the pressure. So this is really, at least formally, a Hele-Shaw type problem. You have this Darcy's law at the boundary, and you have an elliptic equation in a set that is moving with time. Okay. In fact, this is expected to be true if you prescribe an initial data for the pressure, okay? If you think about the original Hele-Shaw problem, it makes no sense to give, well, you can give an initial data for the density. That's the same as giving the region occupied by the fluid initially, okay? Well, but the thing is, if here we prescribe the initial data for the density and you translate this, so if this is fixed and you translate this into an initial data for the density, then in the limit, what you will get is that the initial data converge to the indicator function of the positivity set for P, which is what you have in Hele-Shaw. You just tell where the pressure is positive initially, okay? But the thing is that our model allows for precancer zones, in our model, you still may have that values of rho in the limit that are between 0 and 1. Okay, you may regard them as precancer zones. If you consider this as a phase change model, then this would be called a massive region. Okay, and then well, this is only possible if the initial data already have these massive regions. Okay. The model does not create regions where rho is between 0 and 1 unless they were already present at the very beginning. But the thing is that, okay, there are two things here. The first thing is that the velocity, if you have these precancer zones, will not be given anymore by the gradient of the pressure. Because in fact, you may think, well, if the tumor zone reaches a region where rho was already bigger than 1, you do not need so much energy, so much pressure to make it become cancerous. Okay, it already had developed some cancer. Okay, so you need less energy, so the tumor grows faster. Okay. And on the other hand, in precancer zones, the pressure is 0. So you drop this term here, and then you get an ODE for the density, and it's that one, and then you get an exponential growth for the density. Okay, you can put here a 0 because you're in a region where P is 0. Okay, and then you get an exponential growth until you reach the level 1. When you reach the level 1, things cannot grow more without developing a pressure, because rho and P are related by the Hele-Shaw graph. But let me tell you that then, if we have initial massive regions, the free boundary problem is not enough to describe this limit. You need the density equation. Okay. Okay. And well, so for example, let me explain you what this means. In principle, you could have an initial data which is well below 1. Well below 1. Imagine that this is level 1. Imagine something like this. What happens is that this increases exponentially until it reaches the level 1. When and the pressure is 0 up to this moment, but at this time, this would like to increase more, but it is not allowed to do so. So here you will have a positive pressure. So immediately, instantaneously, initially you don't have something for anything for the pressure, and immediately you get a positive pressure in a big set. Okay, so the pressure is very, very discontinuous in time. Okay. This is not the same for the density. The density, as I told you, the limit is continuous in L1. Okay. So there were several precedents in the case without growth term of this limit when n goes to infinity. First of all, there were cases in which the limit was stationary because there was no source there, and well, then the limit is stationary if you don't have a source. Well, here most of the work is devoted to see how projection takes place, because so they consider initial data which are incompatible with the limiting graph, and then what you have in the limit is a projection onto a mesa, and well, so people talk about the Mesa problem when they talk about m going to infinity. They never identified this as a Hele-Shaw problem because there was no evolution. Okay, but then a bit late, well, quite later, people started to think about non-trivial limit evolutions in principle with sources at the boundary. Okay, so the first paper talking about this was a paper on special subsimilar solutions for porous medium equation. It's a paper by Don Aronson, Omar Gil, and Juan Luis Vázquez. Well, they study phase plane for the profiles of these subsimilar solutions, and they prove convergence to a profile which is a solution of Hele-Shaw. In this case, the source lies at infinity. What they consider is the so-called focusing solution for the porous medium equation. These focusing solutions describe how a hole is filled. So here you have the flux at infinity. So this closes and closes and closes. And well, these solutions are important because they have to do with the optimal regularity for the porous medium. Okay. Then, well, with Omar Gil, we did a couple of papers studying the general case, not only for special solutions, but in this case, we have a boundary where we work in an exterior domain. So we work in an exterior domain. So we have a fixed domain here. Let's call it G, and here the omega of T is kind of an annulus, and here you have a non-trivial boundary data for the P. Okay. Some other people worked on this. Well, several people, in fact, Bogadini, Vida. All these papers, well, this one deals with the profiles, deals with ODEs. These papers deal with weak formulations of the problem as the ones we are considering here. I didn't say it here, but we are considering these equations in a weak sense. But there is another approach using viscosity solutions, and well, there are several papers by Iwon Kim and Sven Jakobsen, Carlsen, several other people. And yeah. Okay. So, well, I will not talk much about this. So, well, there are some estimates which are rather trivial. L-infinity estimates come from standard comparison arguments. And, well, you have L1 estimates that are also more or less standard. You just multiply by the sign of the density and integrate and whatever. Well, these things yield L1 estimates for the pressure and for the density. I mean, yeah. Well, the thing is that, yeah, you get L1 estimates for the pressure since it's a power of rho, and you know that rho is, well, that P is bounded, and both things will yield an L1 estimate for P. Well, the new estimate, the really new estimate, which is very important here, so let me talk about this one, is a semiconvexity estimate. Semiconvexity estimate. So, well, we have a parameter here which depends on the nonlinearity phi, which we assume to be positive. Our assumptions imply that this is strictly positive. And the thing is that we have a kind of semiconvex. Well, if you didn't have this here, this would be a semiconvexity estimate, a control from below the Laplacian of Pm. Such an estimate is well known for the porous medium without a source. In this case, what we do is we are not able to control Laplace P alone from below, but we are able to do it if we add the nonlinearity phi here. What we are able to get in the limit is that this is controlled from below by minus something, this exponential. This is very good because this goes to 0 when m goes to infinity for any positive time, and then you have this term here. Okay. So how is this proved? Well, of course, you have to do all kinds of regularizations, but the thing is that you compute the equation for the W, and there are some terms which have a sign. You drop them. And then, in the end, you get that the W is a super solution of a certain equation, where P can be regarded as a frozen coefficient, and all these things are frozen coefficients, so you have an equation for the W, okay? And here you have a term with W squared, that's nice. And the thing is that the right-hand side of this inequality is a sub-solution for this equation. Okay? Okay, so notice that here you don't have any spatial dependence, so you just have to take care of these two terms. Okay? So this is this really gives a lot of information, this estimate. The first thing is that, well, if you use the pressure equation, which is here, you can write it in this way with the W here. So since this has a sign, and you have an estimate from below for the M, you immediately get an estimate from below for the time derivative of the pressure. Okay? And since there's a nice relation between the pressure and the density, this also yields a nice relation between a nice inequality for the time derivative of the density from below. Okay? And then if you let m go to infinity, okay, this is bad, but here you have the exponential of minus m. This will go to 0, and this is the same in this case. Okay? Remember that the values, the PMs and the rho m's are uniformly bounded. Okay? So what you get in the limit is that both the density and the pressure are monotone for the limit, for this Hele-Shaw limit. Okay? Well, this is kind of a bit nasty from the point of view of modeling, because this prevents the possibility of having cell necrosis. Okay? But well, this includes the model because this necrosis is due to the lack of nutrients, and here we are saying that you have all the nutrients you want. So, but well, and then but the other important thing is that with these estimates from below, you are able, you are able to obtain L1 estimates for the time derivatives of rho and m. Well, if you want estimates for the time derivatives of rho and p. If you want estimates for the time derivatives of p, you have to integrate in time also. Okay. So, yeah, and then the estimates for the gradients of rho and p are easier. You just get an equation for, they are more or less standard. You get an equation for the gradients, you multiply by the signs, and well, and this is more or less standard. And all these estimates are enough to get a strong convergence in L1, which was what we wanted to have. Okay. Okay, I was saying also that the density is continuous, and that the initial data coincides with the limit of the initial data. Okay, so the computation uses the monotonicity. Well, this computation, there are other possibilities, but this is an easy computation once you know that the limit density is monotone. Okay, so you want to show, you take a test function that you will then let go to 1, and you compute the integral of the difference, the absolute value difference of these two things. Since this is monotone, T2 is greater than to 1, we can remove the initial values, and then I can put this as an integral in time of rho t, and then I use the equation, well, the weak form of the equation, these things, and then all these things are controlled, and then you can control this integral. Then what you get here is a constant times T2 minus T1. So, and then you let set that to 1. So in fact, the density is not only continuous in L1, but it's also Lipschitz. Okay? And then once you know this, you have to identify the initial trace. So first, you integrate the equation before passing to the limit against this test function. Then you let m go to infinity. You let m go to infinity. Okay, so this will approach our initial data. This will approach our limit function rho. All these things will be nice. Then you let t go to 0, and then finally you let zeta go to 1. Okay. Okay, so that's a computation, and it's a computation once you have the monotonicity. As for p, as I told you before, it's discontinuous P of t is discontinuous in any LP space, okay? Because you may have all these jumps that make the mass or any LP norm increase a lot, okay? So the best example is maybe this one where the P jumps immediately from being 0 to being positive in a set of positive measure. Okay. Let me talk about another issue, and it's proving the finite speed of propagation for this equation. You would like to know that you really have a free boundary, okay, separating the region where P is positive from the region where it is not. Okay, and then the thing is that we prove that if the initial data have a compactly supported pressure, then this will also be the case for any later time. And well, the idea is, well, you use the equation for the pressure. Here, instead of putting a P, we put 0, since P decreases with, since phi decreases with P, this will be bigger. So we have that this is less or equal than this quantity here. Okay. But then the things that one can check, okay, well, if you take this function, this nice inverted parabola, truncated inverted parabola for with a certain time delay, which is a viscosity solution of the Hamilton-Jacobi equation, this Hamilton-Jacobi equation, it turns out that it is a super solution for this equation here. Okay, it is a super solution as long as you don't let time go by too much. Okay, but then this, which has finite support in all the times up to this one, is controlling the support of the pressure, of your pressure, okay? And the good point is that these quantities, this one and this one, do not depend on the size of, on this constant C. So you may take C as large as needed, so as to put this on top of your initial data, okay? And well, you do this for a short time, and then you do it again by changing this function, and you can prove that the support is controlled all the time. Well, now we come to a different issue, which is uniqueness for the limit. Okay, so you get a limit, but you want to identify it as the only solution of your limit problem. And the thing is, you would like to use Hilbert's duality method. Okay, okay, this is trivial for the heat equation. Okay, and you can do it also if you have nonlinearities that are in the diffusion term that are Lipschitz. But in this case, you have this graph, this monotone graph, which is not Lipschitz at all. Okay. So you need some. We will still use Hilbert's duality method, but we use a trick that we learned from an old paper, which a bit unknown paper by Anne Crowley, which is the following. Well, imagine that you have two solutions of the problem. Well, let omega be a set containing the supports of ρ1 and ρ2 for all times between 0 and t. Okay, we already know that the supports are controlled in time. Okay, so the thing is that this is the distributional version of the equation. For okay, we have a distributional version for the equation for both ρ1 and ρ2. We subtract them and we write them in this form. Here we have the test functions, okay. But then these coefficients. So instead of in the classical idea for Hilbert's duality method is that you have here ρ1 minus ρ2, and then you get an equation with bounded coefficients. You get a with bounded coefficients. You get a backwards in time equation with backwards coefficients for the test function, and then you construct it in a clever way. Okay. So here we cannot do this because if we don't have this here, then the coefficients would not be bounded. So we add also here p minus 1 minus p sub 1 minus p sub 2. Okay? So now the coefficients will be bounded. Okay? Instead of having rho 1 minus rho 2 over p1 minus p2, which is what you would have in the, if you do Hilbert's duality method in the way it's usually done, then this would not be bounded, but we are adding this also. So this is bounded from above by 1 and also from below. Okay. This is also bounded, and this is also bounded. All the three things are bounded. All the three things are bounded. So now, okay, let me go back to this. So what we want to do is we want to solve an equation for this with a certain right-hand side. So we solve, we would like to find a value of psi such that this is equal to A times G. This A is the same one as we had here, okay? With psi equal to 0 in the boundary of omega for all times, and with initial data, which, well, since this is backwards in time, this is the final data, equal to 0 in omega. So that this psi is really an admissible test function. Okay, of course, well, the coefficients are non-smooth, and they're not strictly positive, so you need to perform an approximation, and you have to control the terms. But, well, we have enough properties for the coefficients so as to be able to perform this approximation procedure. So then if you use psi as a test function, what you would have here, you would have rho, okay, let me go to the previous slide. Here you would have rho 1 minus rho 2 plus p1 minus p2 times A times G. But look at the form that A has, so this cancels with the denominator, and then what you get is that the integral of rho 1 minus rho 2 times any reasonable function G is equal to 0. So in fact, this means that rho 1 equals rho 2. Then to obtain uniqueness for rho, you go back again to this equation, but now rho 1 equals rho 2, so a lot of terms drop. In fact, the A drops wherever it is. Okay, and you get this nice equation, and now here you just take psi equal to p sub 1 minus p sub 2, and you use the monotonicity of phi, and you get that p1 has to be equal to p2. Okay. So let me show some numerical examples. Yeah. Okay. So in this first example, we put a specific nonlinearity here, 5 times 1 minus p. On the left, we are drawing at a certain large time, fixed large time, both the density, which is drawn here, and the pressure, which is drawn here. Here, this is done for m equal to 5, and here it is drawn for m equal 40. So as you see, well, in both cases, as it should be, you only have a pressure where the density is positive. You have a positive density, a positive pressure only where the density is positive, since these two things are related by a power. But as m goes bigger and bigger, what you see is that either you have a flat thing close to 1, or you have 0. Okay, and here you have a pressure which has more structure. Okay. Let me, here I have another example. This is just for m equal to 40, and here we are showing the solution at 4 different times. Okay, the thin line is the density, and the thick line is p. Well, we are trying to show here that the pressure and the density carry two different informations. Okay, in the region where p is positive, yeah, both things. I mean, the density does not say too much. But outside this region where rho is between 0 and 1, it evolves on its own and carries different information. So here, well, it cannot be seen, but things are, they are below 1, so this starts increasing. When it approaches 1, it becomes flatter and flatter. Now the pressure is only seen in the regions where the density is close to 1, and where it is below 1, well, where it is well away below 1, it stays close to 0, the pressure, okay? And these things, well, you don't see this very well, but these things are still evolving at a certain, and these things become spreading. Once the pressure becomes non-trivial, this will move to the sides, And at a certain point, the massive regions will disappear, okay? And let me talk about a particular example, that is tumor spheroids. If you have radial symmetry, you can compute things more or less explicitly, according to the free boundary model. Well, you have the domain where the pressure is positive, and well, this is the place where rho is equal to 1. And we are assuming that you have radial symmetry. You have that this is a ball centered at 0 with a certain radius. In this ball, you have this elliptic equation, which is in fact an ODE. You can solve it with boundary data equal to rho of t, r of t. And then you have these geometric motion rules. You can, and well, with all these things, you can just compute. It's possible to prove that there's an R and a P that solve this, okay? And then once you have that, you just define the density at time t like the indicator function of the set where P is positive, okay? And well, you have to prescribe an initial radius for the spherical tumor, okay? The point is that one can show that this function that you build in this way is indeed a solution to our problem, to our weak problem, okay? And in fact, it approaches a traveling wave as t goes to infinity, which has a limiting speed which is independent of the dimension. You can compute it. Well, I'm saying that this is a traveling wave behavior. The thing is that the solution will approach a one-dimensional traveling wave rotated in space. So you have a one-dimensional profile. And here you can see the profile. Here you have the density, which again, this will approach the profile. When this is done for m equal to 40, the profile will approach an indicator function. And here you have the pressure. Okay. So let me go on to more complex models, a bit more complex models. Well, the thing is that, at certain stages, nutrients matter. I mean, you don't have as many nutrients as you wish. In fact, this is in general the case. So you should consider a model which is not purely mechanical. You should add nutrients. So you have this mechanical part, and here you have the Lotka-Volterra type term. Now this nonlinearity will depend both on the pressure and the C, which is the density of nutrients, and you have also an equation for the density of nutrients, okay? And well, these nutrients diffuse according to the heat equation, okay? And well, in this case, we are assuming that that nutrients are supplied at infinity, okay? That yeah. And well, as for the constitutive functions, the phi should decrease with the pressure. If you have more pressure, cells do not reproduce so much. They should increase with the nutrients. The more nutrients, the more you can reproduce. And well, there's a threshold. And well, if you reach the homeostatic pressure, even if you have all the supply of food available, then there will be no multiplication. Okay. Well, and as for the well, so this function tells you how nutrients are consumed, and of course, things that are good for multiplication are bad for the nutrients. Of course. No? So this should decrease with the pressure, and I'm saying that, okay. No, okay, so, yeah, okay, so the biggest the pressure, yeah, the less multiplication, so less consumption of nutrients. Okay, yeah, this is it. So the biggest the nutrients, the biggest the multiplication, so you will have more consumption. So that's the right sign. Okay, and yeah, and finally, if C is equal to 0, then there's no nutrients, there's no multiplication, then you should not gain anything. The good point about this, once you introduce nutrients, is that it may happen that phi of PC, that tells you how the density is increasing, might be negative for C small. And while this allows cells to become necrotic. I mean, they can die, they can disappear. Okay? So at the center of the tumor, the density of tumor cells may decrease. Okay? So this is good to describe early stages for the model. So here we need additional assumptions. Well, of course, we need assumptions on the initial density, which are more or less the same ones as we were assuming before. But here we are not able, in this case, we are not able to obtain a semi-convexity estimate. So we are not able to get good estimates for the time derivatives. So in fact, if you want to get these estimates, you have to impose them on the initial data. Okay. So in fact, what we do is we impose that the initial time derivative is in L1. And we do it in this way. Okay. And we also assume that the initial time derivative for the nutrients is in L1. Okay. So it's an open problem to remove these assumptions. It would be nice. Okay, and well, in this case, we prove a strong convergence in L1 towards BB function, solving the limit problem. And we still are able to show that there's a finite speed of propagation for both the density and the pressure. Of course, not for C, not for the nutrients. They are solving a heat equation, and they will propagate with infinite speed. Okay, and we're able to show uniqueness. Okay, but yeah. Let me talk about another ingredient, which is active motion. As I mentioned, this is a different paper that we did with Nicolas Bochelet and Minh Tang and Benoît Pertam. Here we are introducing a new term, nu times the Laplacian of rho m, which takes into account that sometimes cells move by themselves, not only because of being pressed by, pushed by pressure forces. And well, this is due to random motion of cells. So the important thing, well, there are several issues. I'm not going to talk in detail about this because I'm running out of time. But the thing is that now the potential for the velocity is not the pressure, which is this part. You have to add here a new term that is nu times log rho m. Okay. So when trying to get a semi-convexity estimate, you will get a semi-convexity estimate with something involving this quantity, not only this part. And of course, we'll have to add the phi at some place. But what's the effect of having this diffusion term? You will get more regularity. Yeah, that's regularizing. It's not degenerate anymore before passing to the limit. And you get the same complementarity relation. Complementarity relation, I mean, yeah, I mean that this relation, P times Laplace P plus phi of P equals 0. The same one. So here at this level, you don't see the effect of the nu. That does not mean that it doesn't have an effect. First of all, it gives you more regularity, but second of all, the tumor evolves faster because this diffusion term makes gives long tails for the density far away from the tumor. Okay, the density, the pressure. Okay, the pressure will, the positivity set for the pressure will stay bounded, but this will not be the case for the density, which will become positive everywhere. And so since outside the tumor you already have some density, you don't need so much pressure to move the tumor, okay? And let me just talk about a paper by Benoît Pertam and Nicolas Bochelet that this is a preprint, which has just appeared in archive, in our archive. Okay, here, the difference with the previous models is that when you again have a potential for the velocity, okay, but this potential is not the pressure anymore. The potential is obtained by solving this equation. This is called Brinkman's law. And if I understood it well, the thing is that you have weaker estimates for the pressure, so it is more difficult to obtain a strong convergence for the pressure. And the nice thing about this model is that pressure may be discontinuous in space, though W is not. Okay. And my final slide, well, we are still working on this. In fact, I came this week to work on this with Benoît Pertam and some other people like Antoine Mellet. Next step is proving that P is continuous in space for almost every time. The second thing we think we have succeeded in proving this is that then rho of T will be the indicator function of the set where P is positive and where plus something else if U is below 1, and if U is below 1, here outside the tumor, the density is increasing exponentially, okay? And the thing is that if the initial data, and this is important from the point of view of modeling, if the initial data do not have any massive regions where they are between 0 and 1, then the density will be an indicator function, okay? Well, the next step we are trying to do this is trying to prove that the measure of the boundary of the tumor is 0, okay? And well, other steps that we would like to, but this is much more difficult. We would like to show some regularity for the free boundary. We would like to add other elements in the modeling like self-extension, and well, you can consider different kinds of cells. You can, I mean, the modeling is quite involved. You can do all kinds of things. So that's all I wanted to say. Thanks a lot for your attention.